All right, Algebra 2, as we move into Chapter 7, we're starting with a new type of function here that we have not talked about at all yet this year, and that's something called an exponential function. The second half of this chapter gets us into logarithmic functions, which are going to be totally new, but we're going to start just talking about exponential ones here first. So 7.1 has a title here called Exploring Exponential Models. So what I wanted to do is just kind of start off with an activity right here, and I don't think it's really important that you guys put this in your notes, but I think we can just kind of watch and follow along and see if we get the gist of what's happening. So we're going to raise rabbits here on a farm, everybody, and let's take a look at what's going on here. We're going to start with a population of rabbits, and I wrote this in a weird order. We're beginning with a population of 20 rabbits in what we call t equals 0. And then what's happening is that our population is increasing by 10 rabbits per year. So what I wanted to do here was to just take a minute and say, all right, what's going to happen to our rabbit population? Well, here we are. In year 0, we have a population of 20, and there's no point in talking about the growth here because we haven't been doing this experiment long enough. But after 1 year, where are we going to be? Well, this setup says that our population increases by 10 rabbits per year. So we're going to add 10 rabbits to what we had before and now have a population of 30 after 1 year of raising rabbits. And our growth right here is 10. We've got 10 more rabbits than we had the previous year. And let's keep going. After year 2, we add 10 more, and we're going to have 40 rabbits for a growth of 10 again. And of course, we're going to try to stay positive here, everybody. There's no mention of any rabbits dying off or getting sick or getting old or anything like that. So we're just going to keep adding to our rabbit population. After year 3, 10 more, and we now have 50 for a growth of 10. After year 4, I think you guys are seeing the pattern right here. And I'm going to go all the way to year 5, and we just keep adding 10 rabbits every year. And that's what our table looks like. Not a real difficult pattern to try to see what's happening. So very quickly, let's graph this and see what's going on here, guys. In year 0, right over here, we said we were going to have 20 rabbits. So that's going to be right over there. And then after 1 year, that amount went up by 10. So we were at 30 rabbits, and then 40 after year 2, 50 after year 3, 60 after year 4, and 70, I believe, after year 5. Okay, and that is what our graph looks like. And what I'm sure everybody recognizes right here is that those 6 points that we just plotted are collinear. So when we go to graph a line here of what our population of rabbits is going to look like as a function here of t, we end up with what we call a linear function. And this shouldn't surprise you guys at all. This is the most basic type of growth, or could be decay also, but the most basic type of growth function. And this is what you spent almost all of pre-algebra and algebra 1 working on a couple of years ago. And we spent some time with linear functions back in chapter 2 at the very beginning of this year, but not much. So what I have right here, guys, if I remember, wait a minute, if I remember what that is, yeah, here we go. This is one example here of what a linear growth model looks like. And in a linear growth model, it's the amount of growth, the number of rabbits in this case that we're adding each year that remains constant. And in the graph, that slope right there, guys, of what we're dealing with, that's that growth model. If we were to measure the slope between any 2 points right here, we're going up by 10, and that's the number of rabbits that we have right here, and we're going to the right by 1 year. So the slope of this line is going to be 10 over 1, and that would be rabbits per year. So that's what a linear growth model looks like. But I would ask you guys, if this is what we were dealing with here, does this seem to you like a realistic expectation for how your population of rabbits might reproduce? And I think most of us would look at that pretty quickly and say, no, I don't think that's really what it's going to look like in the real world, not that I've ever raised rabbits. So let's go past this graph right now, and then let's see a new situation right here. Although I just remembered something I wanted to change in this problem here, guys. So before we get too far into that, I'm going to change that 25% into a 30%. Okay. So what's going on here now, guys? A population of rabbits is now increasing instead of by a set number, instead of by 10 rabbits per year, now we're increasing by a percentage, 35% per year. Okay, and again, we're still beginning with a population of 20 in year t equals 0. So let's fill in this table now and graph. So the first line is still accurate. In year 0, we still have a population of 20. We don't have any growth yet. In year 1, we're going to have to take this population of 20 and increase it by 35%. Now, there's lots of different ways to do this, but I would imagine that most of us wanted to learn how to do this in the most efficient way possible. So I'm going to go to my calculator, and again, this is different than the TI-84 that you guys use, but I think this part is going to work identical, and I'm going to have you do something odd at first, guys. I know this doesn't seem to make sense yet. We're going to type in the initial rabbit population, which was 20. We're not going to hit anything else, and then we're just going to hit the Enter button. Now, why did we do that? Because what I'm now going to do is multiply this 20 by a particular percentage. All I'm going to hit, though, guys, I'm not going to type in the 20. I'm going to go directly to hitting the multiplication button, times. And as soon as I do that, you'll notice, and this is true on the 84 as well, that an ANS popped up in front of the multiplication sign. The ANS means last answer. So the last answer that my calculator gave me was this 20 over here on the right. Now you'll see why we did that in just a second. Now, what a lot of people want to do is multiply the 20 by 0.35. You've always got to change percentages into decimals, and that's how you do this one. But if I were to hit enter right now, all that's going to give me is the growth, the number of rabbits that we've now added to the previous population. And in my next step then, I'd have to add that to the original 20. So here's a sharper way to do it, guys. Rather than 0.35, we're going to multiply it by 1.35. What we're really doing is taking 135% of the original population of 20 rabbits. What that will do is in one step, it'll keep the original 20 rabbits and then add an additional 35% to that. So when we hit enter, we get 27. Now, I'm going to come back to this page here, but let me go ahead and write this down. So according to this model, after 1 year, we now have 27 rabbits for a growth of 7. Now, here's the reason I had you do some of that weird stuff just a second ago. All you have to hit now, both on my calculator here, but also on your TI-84, is hit enter one more time. When you do that without typing anything else in, it takes the previous equation, or the previous entry, and simply repeats it. Now, on your calculator, instead of 27 on this left-hand side, it would have shown up as ANS, and that answer would have been in reference to the 27 that we had just a second ago. So the cool thing is here, guys, all you have to do is just keep hitting enter over and over and over again. Now, maybe not surprisingly, I ran into a little problem. How do I have 36.45 rabbits at the end of a year? And the answer is, when you're talking about something like a living creature right there, guys, we are not able to do that with decimals. So we're going to have to round this to the nearest whole number, and I'm going to go with 36. Now, that's going to skew our answer just a little bit here, but that's okay. So after year 2, we're going to have 36 rabbits, and the jump from 27 to 36 is 9. Now, as I said before, guys, all you have to do is just keep hitting enter here. So here we go. After year 3 now, we're going to be at 49. And then it looks like 66, and then it looks like 90 if we rounded that to the nearest whole number. So let me make sure I got that right. 49, 66, and 90. All right, so 3 is 49. 4, we're going to have 66 rabbits, and after year 5, we're going to have 90. And the amount of growth from 36 to 49 is going to be 13 rabbits of growth. From 49 to 66, we're adding 17, and then from 66 to 90, we're adding 24 rabbits each time. So what I think is obvious now is that this amount of growth right here is actually increasing from year to year. Unlike the linear model, if I go back 2 pages, everybody, where the growth amount stayed constant every year, now it's the growth percentage that remains constant every year. But that means that the amount of growth is actually going to change. What I want to do here, guys, is I'm going to go back to this graph that we had here just a second ago, and I'm going to try to plot these same numbers here, or excuse me, the new numbers here for our population of our rabbits on the same graph. So let's see what this one looks like. With this second model, at the first year, I should say at t equals 0, we were still starting at 20. Then after the first year, I think we had 27 rabbits after that. And then following the 27, we had 36. So let's see, year 2, 36 would be right about here. Now, at this point, I would ask you guys to think about this. Which growth model seems to be increasing our rabbit population faster? And it certainly seems like what we have in purple is going to outpace what we have in green. And that's the case for the first couple of years. But some interesting things starts to happen here. When we get to t equals 3, we're now at 49 rabbits. So 3, and then let's see, 10, 20, 30, 40, 49. That is just a hair under the 50 that we had in the linear model. Then at year 4, we're up to 66 rabbits. 66 is going to put us right about there. So for the first time now, guys, the number of rabbits we have here in this second model is now greater than that in the first. And I think you can see what's happening now. After 5 years, we're now going to have 90 rabbits, as opposed to the linear model where after 5 years, you only had 70. So let me think. This was 70 right here. This is 80, and 90 would be up here somewhere roughly. So at the very end of this graph, we are roughly right about there. So what I'm hoping you guys can recognize is that what we're dealing with in green is not a linear growth model like what we had in purple. What we're dealing with here is a curve that's increasing, but at an increasing rate. That, everybody, is what we call, hang on a second, let me move this, oh, that's not what I wanted. Let me move this linear line that I put right there. Never mind, it doesn't want to happen. I'll just erase that. What we're dealing with here in green is what's called an exponential growth model. And we'll talk about what that means in just a second, as opposed to what we had originally here in purple, which is what we call a linear growth model. Now, I'm not going to say that this is going to happen every single time, but it is pretty common and fairly typical here that a linear model might actually grow faster than an exponential model at first, but eventually that exponential model is almost always going to take over the linear model and give you more rapid growth in a long enough period of time. So this right here, guys, is what we call an exponential growth model, as opposed to a linear growth model that we had in that first example. Okay, so that's what's going on right here. In a linear growth model, you're always adding the same amount right here. You're adding 10 each time. And in this exponential growth model, what we're doing instead of adding is multiplying by the same number each time that we do this. So that, everybody, is a pretty good preview of what we wanted to talk about right here. An exponential growth function is one that, all right, it goes by a lot of different forms, and that might frustrate you guys a little bit, but this is probably the most basic. Every new one that we introduce is going to be a slight variation on that. Y is equal to A times B to the X power. Now, as you can probably tell from the name, it's called an exponential function because this function contains an exponent. But this is different than functions we've dealt with earlier this year. Like, for example, y equals x squared is the most basic quadratic function that you can come up with, and we've seen that a lot. We spent all of chapter 4 dealing with quadratics. The difference here is that in this type of function, a quadratic function, the base is your variable and the exponent is a constant. What we're dealing with here, guys, is that the base of your exponent is now going to be a constant. I can't spell. Constant. There we go. And it's the exponent right here that's going to be the variable. And that's something new that we have not seen at all yet this year. And in fact, I believe, I could be wrong here, I don't think you guys have seen exponential functions at all. Maybe you saw them 2 years ago in Algebra 1, but probably not since. And I kind of doubt you remember them, even if you did see them there. So, let's talk about what this exponential function does. Y, the left-hand side of this equation right here, is the final value, whatever it is that you're measuring. So for us, that might be our final rabbit population. A is the initial value of whatever it is that's growing or decaying here, how much you started with. So A, you'll notice, everybody, is not the exponent, and it's not the base of the exponent. A is the coefficient that gets multiplied in front of that. B then, which is the base of the exponent x here, B is what's called the growth or decay factor here. That tells us basically how quickly this function is changing over time. So this is one of, and by the time we get done with this section, there are going to be 3. This is one of the forms of an exponential function, and probably the most basic out of all of them. Just a quick little table right here that we probably ought to put into our notes right here is whether we're talking about growth or decay. An exponential function can really model either of those two things. Now, everybody understands what the word growth means. That's an object that gets bigger, or I should say a quantity that gets bigger over time. Decay is just the opposite of that. That's a quantity that is going down over time. So notice here, guys, we've made a little table with 2 columns and 2 rows, and that created 4 cells for us right here. We're not really filling anything in right here. So we want to know what's going to happen here, guys, based on the sign of x and then the value of b. So in most cases, I'd say the more common ones right here, we're going to be dealing with this first box right here where x, which is your exponent, is going to be greater than 0, which means that x is going to be positive. Now, when x is positive, and when b, the base of that exponent, is bigger than 1, that, everybody, is what we call a growth model. That's going to be an object or a function or a quantity that is going up over time. But a couple variations can happen upon that. If that base value were smaller than 1, that actually has the opposite effect, and that means that we're actually dealing with a decay function, one that's going down over time. Okay, now you'll notice a third possibility here. B could be greater than 1, B could be less than 1. A third possibility, and I wouldn't bother putting this in your notes, is what happens when B is equal to 1. Now, if you think about that, let's think about a function here where b would be equal to 1, like y is equal to, I don't know, pick an a value, 5, and let's multiply that by 1 to the x power. Well, this is going to be really boring here, guys, because if I made a really quick table, what happens when x is 1? 1 to the first power is 1 times 5 is 5. When x is 2, 1 to the second power is still 1 times 5 is still 5. When I take 1 cubed, that's 1 times 5 is 5. In this case, there's no growth or decay. The function stays constant, and that's really boring. We never really talk about that. So anyway, that's the third possibility. Now, how about down here on the bottom, guys? What happens when your b value is greater than 1? Normally, that would be a growth model, but if your x value here, your exponent, were actually negative, that would have the opposite result then. This would be a decay function, something that's going down over time. But kind of like your mom taught you, 2 wrongs make a... No, mom probably told you to do 2 wrongs didn't make a right. Anyway, when both of these things flip here, guys, when b is smaller than 1 and when x is negative, that actually then is kind of like the opposite of a decay model then. Now we're back to growth, something that's increasing from left to right. So this little table might help you guys out as we move on later into this section. So, with all that in mind, before I move on to graphing, I just wanted to go back and talk real quick about those 2 models that we had right here. This model here, guys, this linear growth model, would probably look something like this. We know that it's linear, so we know we need a slope and a y-intercept. So we're going to have y equals, and it's the slope of this function here, guys, that is modeled by its growth. So that's going to be a 10x, and we would add to that its y-intercept, the value you get from y when x is 0, and that's going to be a 20. So this is something we did back earlier in the year, not really a big deal. This model right here, though, okay, we just wrote it down, guys. It would normally be of the form y is equal to a times b to the x power, where a is the initial amount, right? That's what we wrote down right over here. A is the initial value. So in this experiment, we started with 20 rabbits, so that would go right over here, and we would multiply that by b, and b, we said, was going to be your growth or decay factor. So for us, that's the 1.35 that we were typing into our calculator, and we could just put an x power right there, and that is the function that models what it is that we're dealing with right here. Okay, so, that's kind of something you can look at there pretty quickly and come up with that. All right, let's talk about what the graph of an exponential function looks like. This is the first big thing we want to try to get a handle on as we move on into this section right here. Y equals 2 raised to the x power. Now again, this is new for you guys right here, but what makes it exponential is the fact that we have a variable located in the exponent. And I want to remind everybody, even though you don't like it, that every single time that you learn a new style of function, a table can always be used to get the general sense of what this graph looks like. We won't do this too often, guys. Eventually we'll start to learn some patterns and apply those, but real quickly, let's play around with this. I'm going to go, and just so this is in some order, I'm going to go 3, 2, 1, and 0 for my x values. And let's go ahead and fill those in and see what happens. And I'll do it in this order. When x is 3, we're going to take 2 to the third power. Now, we just came out of chapter 6 where we were dealing with perfect squares, perfect cubes, all that stuff, so we should know what we're doing here. 2 to the third power is 8. So that gives me the ordered pair 3, 8, and this graph passes through that point. Now, when x is 2, 2 squared is going to be 4, so we're at 2, 4. And I would ask you at this point here, guys, do we know what this graph looks like at this point? And pretty clearly the answer is no. Okay, we need to keep going because after 2 points, every function looks linear. When x is 1, 2 to the first power is equal to 2. So we get the ordered pair 1, 2. And at this point, I would ask you guys, does this look like a linear function or not? And the answer to that is pretty clearly no. There is not one line that passes through 2 of those points that also contains the third point as well. All right, there'd have to be another line here that goes there, and no, this is not a linear function. So I want to keep going with this, although we're at kind of a tipping point right here. What happens when x is 0? So my question for you guys is, what is 2 raised to the 0 power? Not everybody knows this, so let's talk about what we're looking at here, guys. Mathematics is nothing but the study of patterns. And if you feel pretty confident about the 3 ordered pairs that we have in our table so far, we should be able to predict what's going to come next. How do you get from 8 to 4? Now, I think there's 2 good ways to answer that. You could either subtract 4, 8 minus 4 is 4, or you could divide by 2. 8 divided by 2 is 4. But only one of those 2 methods is repeatable to get you from 4 to 2, and that's the division method here. So that's what's happening. Every step along the way, we're dividing by 2. 8 divided by 2 gets us 4. 4 divided by 2 gets us 2. So if I'm not sure what 2 to the 0 power is, I just keep dividing by 2. And 2 divided by 2 is 1. So that's something that people get wrong a lot early on in chapter 7. A lot of people think that a number raised to the 0 power is 0. That's incorrect. Any number raised to the 0 power is 1. So that gets us the ordered pair 0, 1, and this is where we stand right here. Now, when I ask in class, hey guys, let's look at these 4 dots, what does it look like we're dealing with? A lot of people want to tell me that we are dealing with a parabola. And I can certainly understand why you would think that, because if we were to connect those dots, it's going to look something like that. And a lot of people now say, all right, and it's going to do the same thing over here on the left side, because I know what parabolas do. Well, kids, that would be what we call an assumption. And that's something we don't like to make in math. So let me go ahead and try to continue this table into a weird spot. Can we put negative numbers in for x in our domain right here? So now the question is, what's 2 to the negative first power? Well, maybe you know where I'm going with this, guys. The pattern never changes. Each step along the way, we simply take our previous answer and divide by 2. So to get 2 to the negative first power, we're going to take 1 and divide it by 2, and that's going to get us 1/2. 1 divided by 2 is just 1 over 2. So now we have the ordered pair negative 1, 1/2. And that parabola that I drew just a second ago doesn't quite look so accurate. How about negative 2? The pattern never changes. We keep dividing by 2. And 1/2 divided by 2. Guys, think of a football game. What's half of a half called? That is 1/4 or 1/4. So negative 2 1/4 is even lower. And just for fun, let's put in -3. And I'll say it one last time, the pattern never changes. 1/4 divided by 2, that's going to get us 1/8. And the keen among you will notice there are some connections right here, guys. 3 and -3 are obviously opposites of one another. The 8 and the 1/8. Now, wait a minute. The word opposite doesn't apply here. 8 and 1/8 are reciprocals of one another. Just like 4 and 1/4 are reciprocals, 2 and 1/2 are reciprocals as well. So that happens every time when we're dealing with negative exponents. Let's try to remember that. Now, if we kept going on this graph a little further to the left, what you'd probably see right here is that these y values keep getting smaller. We keep dividing by 2, so the next one would be 1/16th, and then 1/32nd, and then 1/64th. Those numbers are getting smaller and smaller and smaller, and they're approaching 0. But are they ever going to get there? Are we ever going to be able to take 2 to a power and get it to equal 0? The answer to that is no. And likewise, they'll never become negative either. So we get to see something interesting here, guys. A graph that gets closer and closer and closer to the x-axis, but never gets there and never crosses it. All right, so everybody, what we are dealing with right here, I'd like you guys to put this in your notes right here, is the parent graph for an exponential growth function. Y equals 2 to the x is the most basic exponential growth function that we can come up with. But we got to talk about a few unique aspects of this graph here. For starters, the x-axis has a funny name right here, guys, and it has a purpose within this graph. So I'm drawing it with a dotted line right here. And what we are dealing with is something called, we're going to go ahead and label this right here, a horizontal asymptote. ASYMPTOTE. I needed to spell that out loud for my benefit and not for yours. Now, when you get to calculus, everybody, the definition of a horizontal asymptote changes just a little bit. But for our purposes right now in Algebra 2, we should probably write this down. A horizontal asymptote is what I like to call a guideline. It's not actually part of the graph, but it is something that we like to draw to show us how to draw it. It's a guideline that your function, and I'll just use fxn for function right here, approaches. Okay, and that's the important word here. Approaches, but never touches. I should say never reaches, but let me go with that. Never touches or crosses. Okay, that right there, guys, is a pretty good Algebra 2 definition for what a horizontal asymptote is. And hopefully that line then makes some sense as you guys look at that. The blue curve gets closer and closer to that line, but it never touches it and it never crosses it. Okay, so now that we've got that sense here, I wanted to talk about a few different things. I guess we just discussed asymptote, so let me go ahead and do that. A horizontal line always has an equation of y equals, and then this number back in chapter 2 we called b. Now let me not write that here. B is the y-intercept of that line. Well, that red line passes through the origin, so that's the equation y equals 0. Let's go back up to the top now. Domain is the set of all x values that you can put into a function and get a real result out for y. And this is something, at least this year anyway, we just got done talking about in chapter 6. This graph goes forever out to the left, and it will eventually go forever out to the right. The domain here, guys, is all real numbers, just like the domain of a cube root graph that we just finished up at the end of chapter 6. The range, though, is asking you how high and how low does this graph go. We're talking about y values here, not x's. Well, what I think you guys can see is that this graph keeps getting higher and higher and higher and will continue to do so. There is no maximum value to an exponential growth function. There is, however, a minimum value, and it has to do with the horizontal asymptote we spoke about just a second ago. This graph doesn't go down towards infinity. It never gets to 0, and it never gets lower than that. So our range is that y exists above the line y equals 0. So y is greater than 0 is our range. You'll notice there, what did we omit from the range? 0 doesn't exist, and negative y values never exist. And the last question here, what's the y-intercept? This thing crosses the y-axis right there at a value of 1. That'll become important a little bit later on. Okay, guys, so let's make sure we have this in our notes properly. This is our parent graph for y equals 2 to the x. Now, we spent a long time on that one graph there. The rest of these should go much faster, you guys, because I think we've made some progress here recently as to how we're going to come up with transformations of most of our graphs. For starters, let's take a look at this one. Y equals the opposite of 2 to the x. Now, what I really could have done right there is put parentheses around 2 to the x and the negative out in front. And what I'm hoping you guys remember is that any parent graph, when you put a negative in front of the whole thing, simply gets reflected over the x-axis. Okay, so this transformation right here, we would just say is a reflection. Usually in is the word, but I think over is a little bit more useful. A reflection over the x-axis. Now, one thing I like to do a lot, up to you if you want to do this or not, is draw my parent graph with a dotted line looking something like this. There's the parent graph we just came up with, but now it's being reflected over the x-axis. So instead of hitting this point right here of 0, 1, now it flips downward to the point 0, -1. And I believe then everything that I need to know is right here, and this graph is going to look something like this. Okay, it wouldn't be the worst idea in the world to test maybe 1 or 2 points here. Like, for example, I think we see the point 0, -1 is on that graph. Let's make sure that's right. What's 2 to the 0 power? 1. And then the opposite of that is -1. Okay, good. I didn't draw it super accurately, but I believe I should have hit the point right here of 1, -2. Let's try that one. 2 to the first power is 2, but the opposite of that is -2. Yeah, I think we're in good shape here, guys. So let's answer these questions here in red. Domain, just like before, this graph goes forever to the left, and it will go forever to the right. So once more, your domain is all real numbers. Range. How high does this graph go? We still have this borderline asymptote right here at 0, but this thing goes down towards infinity. We can see that right here. So in this case, your y values are still bordered by the x-axis, 0, but this graph exists entirely below the x-axis. So y is less than 0 is going to be our range for this graph. Asymptote, just like before, is the line y equals 0. Once again, guys, that's the x-axis right there. And the y-intercept, where does this graph cross the y-axis? Right there at -1. Okay, so hopefully that one went a little faster and a little easier for you. Let's try a third case. And this one, there we go, is y equals 2 to the -x power. Now, just coming out of chapter 6, when we were doing square root graphs, I may have talked about this just a little bit with you guys in that case, but I might not have. So let's take it back to square one. What's happening right here is that we have 2 to the -x power. There's a negative, but applied not out in front of the 2 like it was in the last problem, but rather up here directly on the x. And what that does for us, guys, this is now a horizontal reflection. So we would say that our transformation right here is a reflection. This one now is going to be over the y-axis. So just like before, I very often like to draw my parent graph, which looked something like this and this and this. Okay, so there's my parent graph of y equals 2 to the x. Now this graph is being reflected horizontally over the y-axis. So any point that was on the y-axis, like 0, 1, doesn't move at all. But now this graph is going to go up on the left-hand side. Okay, looking like that. Okay, there we go. And now on the right side, it should get lower and lower and lower and begin to approach the x-axis, but never quite hit it. Now again, never a bad idea to test and make sure you're right. I still have the ordered pair 0, 1. Let's do it. X is 0, the opposite of 0 is 0, and 2 to the 0 power is 1. So that one works. How about this guy right over here? -2 4. Let's try it. If x is negative 2, the opposite of negative 2 is positive 2, and 2 to the second power is 4. Check. That one works out as well. I think we got this one, guys. What's our domain? Again, this goes all the way to the left towards negative infinity and all the way to the right towards positive infinity. So our domain, once again, is all real numbers. The range? We're cut off at the x-axis yet again. So that's going to give me a y and a 0. And where does this graph exist? Above or below the x-axis? Only above it, so its y is greater than 0. The asymptote, once again, is y equals 0, and the y-intercept, that same spot where it crosses the x-axis, that's going to be positive 1. Okay, so those are 3 variations on that particular graph over here. And I wanted to give you one more, but I kind of thought maybe we would make that a little bit more interesting. So I tell you what, guys, we're going to change this problem around just a little bit, and we're going to make it y equals. And I think this time, guys, I want to go with, I'm going to put a 1/2 out in front here. I'm going to stick with 2 for the base of my exponent here, and then I'm going to make that, let's have some fun with this one. We're going to make this an x plus 4, okay? And then I think we're going to put a minus 3 at the end of all that. All right, let's take the kid gloves off and let's see what this thing can do right here. Okay, guys? So what's going on in this problem right here? All right, there's a lot happening right here, including a couple of pretty major shifts right here. First of all, the minus 3 at the end, I haven't shown you one like this yet today, but in previous chapters, you guys have talked about this a lot. What a minus 3 at the end of a function always does is it moves everything down 3 units. How about the plus 4 here that's acting directly on the x? That, you guys, is a horizontal shift. And horizontal shifts are always backwards of what you might think. That's going to move our graph to the left 4 units. Interesting. And then this 1/2 value out in front, that's the a value that kind of gives you the slope right here. But let me hold off on that idea. Now, listen, there's a lot going on in this graph. So I think it would be a really good idea, if maybe not to make an entire table, maybe to just come up with a few key points right here and just see what happens. Now, you might be tempted here, guys, to let x equal some of the normal numbers that you would, but I'm going to try to be a little bit sharp about this. I'm going to pick negative 4 for my first x value. Now, why in the world would I pick that? Well, remember that in all these functions so far, your domain is all real numbers, which means you can pick anything you want. But the benefit to negative 4 is that the first thing I'll do is put that right here. Oh, and negative 4 plus 4 makes this new power 0. And now let's follow order of operations. 2 to the 0 power is 1. Let's multiply 1 by 1/2, that's 1/2, and 1/2 minus 3 is negative 2.5. That's interesting. So 4 to the left, 1, 2, 3, 4, 2.5 units down would get us right about there for a starting point. Okay, kind of interesting. I'm going to pick maybe 2 more. How about negative 3? Let's see what happens there. Negative 3 plus 4 is 1. 2 to the first power is 2. Half of 2 is 1, and 1 minus 3 is negative 2. So we're at negative 3, negative 2 right over there. Okay, that's kind of interesting. And I think at this point, let's have some fun. Let's let x go ahead and equal 0. 0 plus 4 is 4. 2 to the 4th power is 16. Half of 16 is 8, and 8 minus 3 is going to get us 5. So 0, 5 is going to be right over there. Now, with those 3 points, guys, I'm kind of hoping you get a general sense for the shape right here, but I think it would probably be a good idea to talk about this before we draw anything else. Now, in all of the previous 3 graphs that we've done, the asymptote, make that just a little smaller so you can see that, has been the line y equals 0. That happened here in the first case, the parent graph. It happened right here when we reflected it over the x-axis, and it happened right here when we reflected over the y-axis. Now, in this case, that asymptote would have started off at the y-axis, but I think you can tell based on the location of those 3 blue dots, this thing is definitely going to cross that line. What happens here, guys, is that just like everything else in this function, this minus 3 moves everything down 3 units. So if our asymptote normally would have been right here at the x-axis, we're going to move that down 3 units as well, and it's going to give us that line right there, which I'm going to redraw looking a little bit better. 3 units down from where it normally would have been is this horizontal line right here, which is y equals -3. Now with that in mind, guys, now that we've drawn the asymptote, now I feel a little bit more confident in drawing my exponential growth curve that's going to look something like this. Okay, so that's what this graph is now going to look like. It's basically an exponential growth curve, but it's been shifted left 4 units, down 3 units, and then that 1/2 actually kind of compressed the graph, although it's really hard to tell that from right here. Okay, let's knock out the other 3 questions. Domain, once again, you can put in any x value you want here, all real numbers. The range is always relative to the asymptote. Our y values exist on one side or the other of the line y equals -3. And which is it, guys? Above or below that line? This graph exists above. Y is greater than -3 is our range. And the y-intercept is where this thing crosses the y-axis here. That's going to end up being 5 just in this particular case. All right? All right, so everybody, that's as much as we were going to do for graphing exponential functions. Your first homework assignment in 7.1 deals with that, so you'll get a chance to practice that skill here pretty soon. I'll come back in just a moment and start the second video, which is where we start seeing a lot of word problems, and we start to see what exponential growth and decay functions are really useful for out there in the real world. All right, guys, good luck on the start to 7.1.